Welcome to another explainer. I am absolutely thrilled you're here today because we're going to unpack something that is honestly kind of like magic. Think about what happens when you walk into a dark room. You reach out, you flip a switch, and bam, instantly the room is bathed in light. We do it dozens, maybe hundreds of times a day without even a second thought. But behind that incredibly effortless action is a massive, super intricate journey. So today, our goal is to map out that exact journey. We're going to track a single batch of electrical energy from its very birth all the way to its final destination right there inside your home. Okay, let's dive into this itinerary. First up, generating the spark. Then, the high-voltage highway. Next, stepping down to neighborhoods, inside your walls, and lastly, completing the circuit. So, starting with Section 1, generating the spark, where power is actually born. Now, we harness raw power from a huge variety of sources. We're talking renewable sources like the blazing heat of the sun, massive wind currents, or the relentless force of flowing water crashing through a dam. Then we've got thermal power plants burning coal or natural gas, and even the literal atomic reactions happening inside a nuclear plant. They all look completely different, right? But here's the secret. With the exception of solar panels, almost all of these diverse sources serve the exact same fundamental purpose. Their ultimate job is just to create enough mechanical energy to turn a massive turbine. That's the whole shebang. But why do we need to spin a turbine? Well, to achieve electromagnetic induction. I know it sounds like a heavy textbook term, but imagine zooming deep inside a massive generator. You've got these giant turbines spinning at just incredible speeds. And as they spin, they rotate huge magnets around coils of copper wire. This spinning magnetic field literally pushes and pulls on the electrons inside the wire, causing those glowing little electrons to move together in one uniform direction. And that organized movement, that is electric current. We've just converted mechanical energy into electrical energy. The spark is officially generated. Which brings us to Section 2, the high-voltage highway, high-speed travel. Okay, so now that we've created this raw electrical energy, we actually have to move it out of the power plant. And if you take away only one thing from this section, let it be this. Electricity absolutely hates traffic. Seriously, when it travels through wires, it encounters resistance, which basically causes it to lose energy in the form of heat. To solve this, power plants use a device called a step-up transformer. Think of it as a supercharged on-ramp to a massive high-speed expressway. By drastically increasing the voltage, which is just the pressure pushing the electrons, the electricity can travel super fast and efficiently over incredibly long distances with barely any energy loss. Moving right along to Section 3, stepping down to neighborhoods, slowing things down. Up until this very point, the electricity has been racing across the country at hundreds of thousands of volts. We're talking about massive high-voltage transmission towers, carrying glowing power lines across towering mountains, dense forests, winding rivers, and harsh deserts. The sheer scale of this infrastructure is just mind-boggling. But there is a stark contrast when we look at our daily appliances. The devices in your home only require about 110 to 120 volts, or 220 to 240, depending on what country you live in. If you tried to plug your television into a transmission line carrying hundreds of thousands of volts, it would be instantly destroyed. No question. So this presents a really crucial engineering dilemma. How exactly does a roaring 100,000-volt current become tame and safe enough to charge your fragile little smartphone? The grid desperately needs a way to hit the brakes. And the answer lies in substations and local transformers. If the step-up transformers from earlier were the on-ramps to the highway, well, these are the off-ramps. As electricity approaches a city, it enters a large electrical substation, where step-down transformers significantly reduce the voltage. From there, it travels through distribution power lines. Those utility poles and underground cables you walk past every day. As it finally reaches your street, a local transformer, which is often that gray cylindrical box mounted on a pole, drops the voltage one final time down to that perfectly safe household level. Now, the electricity is finally ready to enter your home. It travels down a service cable and passes directly through the electric meter. This is literally the exact moment the utility company hands the baton over to you. The meter just sits there, quietly tallying up your electricity consumption so the power company knows exactly how much of that massive journey they facilitated for you. Next up, Section 4, inside your walls, navigating hidden paths. So before the energy can actually go anywhere inside, it has to pass through a vital security checkpoint, the main electrical panel, or as you probably call it, the breaker box. This panel is filled with circuit breakers, and their entire job is to just stand guard. If a wire suddenly draws way too much power, say there's a huge overload or a short circuit, the breaker immediately trips, physically cutting off the electricity. It's a brilliant safety mechanism that stops the hidden wires inside your walls from overheating and potentially starting a fire. Once past the breaker box, the electricity travels through a really specific configuration of wires. And this brilliantly illustrates how the whole system balances immense power with safety. You have the live wire, which brings the active high-voltage power right into the appliance. Then you have the neutral wire, which completes the loop and returns the used power back to the panel. And finally, there is the earth wire, or the ground wire. If something goes terribly wrong and loose electricity touches the metal casing of, say, your washing machine, the earth wire provides a safe alternative path straight into the literal dirt outside, protecting you from a deadly electric shock. And finally, Section 5, completing the circuit, the microscopic mechanics. Let's see how all this builds into the action we talked about at the very beginning of the explainer, flipping a switch. When the switch is off, there's a literal physical gap in the wiring inside your wall. The electrons are just backed up, waiting. In step 1, as you flip the switch, a tiny metal bridge snaps into place, closing that gap and completing the circuit. In step 2, the current instantly rushes across that bridge. And in step 3, the electricity reaches the bulb and boom, it lights up. The whole thing happens in a fraction of a millisecond, but it is a distinct 3-step mechanical process. And it's not just a light bulb. This exact complex journey safely powers literally our entire modern existence. The energy that started by crashing through a giant dam or spinning a turbine from atomic heat is right now quietly buzzing behind your walls. It's powering the lights above you, the fan keeping you cool, the TV humming in the background, the fridge preserving your food, the computer you work on, and the charger feeding your phone. The grid safely delivers this energy to millions and millions of people every single day, completely without fail. So, I want to leave you with this final thought. What if you had special glasses that let you actually see this invisible infrastructure? Just imagine looking out your window and seeing rivers of glowing energy racing from distant power plants, rushing down high-voltage highways, trickling through neighborhood transformers, and finally branching out into the walls of every single house on your block. It is a literal, instantaneous, invisible miracle happening millions of times a second all around us. The next time you flip a switch, I really hope you take just a brief second to appreciate the incredible journey that made that light possible. Thanks for learning with me today on this explainer, and I will catch you in the next one.